Good afternoon, I'm Mr. Ish. Thank you for joining me. A very interesting video because we will relate the energy to force and position of an object that's moving in a straight line. Remember, linear motion or motion in a straight line, relating here energy to force and position. Everything will come about with regards to a moving object by means of two equations. One is kinetic energy is equal to half mv squared. You know that equation. The other one will be force is equal to mass times acceleration. The units of kinetic energy is joules, the units of force is newtons. How can we relate both of these concepts to one another and bring in the position? Think about an object moving in a straight line having a certain final velocity with an initial velocity and acceleration times time. If the initial velocity is equal to 0 meters per second, this equation becomes final velocity, or you can just say velocity is equal to acceleration and time. All you have to do is take this and substitute it right here in place of v. What do you end up seeing? You get Ke, or kinetic energy, is equal to half mass times acceleration times square. You see, this is my velocity square, which is equal to at. You can open this up. You'll have half mass times a square t square. If you shuffle these things around, what happens? You'll have half. I'm plucking out a single mass and a single acceleration, and I'll get that mass acceleration. Then I'll still have another a, which is acceleration and time square. Mass and acceleration, I'm left with that a and then the t square. This mass and acceleration, which is coming about from right over here, is the same thing as that force. You end up seeing half force at square, or you can say is force times at square over 2. This right here is equal to your kinetic energy, so you've related energy to force. Now how do we bring the position item in here? You know, position is symbolized as the S. How can we bring position? Well, you know, I'm telling you, we're working here with an object that's moving in a straight line, but what if that object were dropping down in a straight line? You know, there's a specific function here, S is equal to half at square, where a can also be gravitational constant. A moving object in free fall, position of that object is half at square. Well, I'm seeing a half at square here, aren't I? You have this half at square. So suddenly you can bring in that position. Position in all instances is equal to half at square. We have a half at square here. So kinetic energy is equal to force of an object and its position. And now you're relating the joules to newtons and meters. So joules is equal to newtons meters. If you were to Google energy, one of the units of energy is joules, but another unit of energy is also newtons meters in a product relationship. And that right there is exactly where it comes from. Kinetic energy of an object is equal to force on that object multiplied by its position. It's also equal to force of an object times at square over 2. Kinetic energy is also equal to half mv square. So you're seeing everything here being derived for you in a rather interesting and seamless manner. With this factor coming into play, final velocity is equal to initial velocity plus acceleration times time, where the initial velocity is 0. You have final velocity, or just velocity, equal to acceleration times time, and you fit that in and you go from there. And that's right there is the end of this video. Have a good day.